So, continuing with the monthly lecture series, today CSIR IPU brings you the second lecture in the series on innovation in advanced functional material by Dr. P.K. Panda, a chief scientist, NAL Bangalore. I, Dr. Balu Verma, am accompanied by my colleagues, Dr. Lipika Patnaik and Dr. Ajita Agarwal. We will be hosting this program today. Before I start the program, I will it is my privilege actually, that I introduce Dr. P.K. Panda, who is a chief scientist with NAL. Dr. is a scientist par excellence, having a PhD in material science, and he has been working with NAL since 1993. He's heading the division of material science in NAL. His specialization is smart materials, preparation of PZT and lead-free piezoceramic fabrications of actuators, sensors for aerospace vibration control, energy harvesting, nanofibers for water filtration application, and so on. He has 9 patents to his name and 97 publications in peer-reviewed journals. He's a recipient of several awards. Notable amongst them is Professor Satish Dhawan Young Engineer Award, NAL Young Scientist Award, AICTE INAE Distinguished Visiting Professor Award, and so on. He has international collaborations in a number of countries, including Germany, France, Russia, Singapore, and Portugal. I would now like to invite Dr. P.K. Panda to give his lecture on innovation in advanced functional materials. Dr. Panda, please.
Thank you very much, madam. Good morning to all. I would like to share the slides first, and then I will proceed.
Yeah, please.
प्रॉब्लम ये होती है कि 5 ह्यूमिडिटी के पॉइंट हम देते हैं ना, तो वो 5 टेम्परेचर अलग अलग लेके 5 ह्यूमिडिटी के पॉइंट कर लेते हैं और उसको बेस इंटरप्रेट करके गलत तरीके से यूज करते हैं।
25 पे आपने 95 दिया है, हमें 40 पे 95 चाहिए तो अलग उसमें मानेंगे,
अलग मानेंगे।
I would like people to please shut down their mics because you are audible on the line. Please, if you are talking, please put off your mic.
Is it visible, the slides? Hello? Is it audible and visible, the slide?
Yes,
go ahead.
You are audible and the slide is visible. If you move them, we'll get to know whether it is moving or not. Yeah, you may continue.
थोड़े क्या मतलब सबसे हाईएस्ट होते हैं।
I would like NPL to shut down their mic, please. Yeah. Dr. Panda, please continue.
Yeah, I'll just take, okay. So once again, good morning to everyone. Thank you very much for introducing. So I would like to thank CSIR IPU for providing me this opportunity to deliver this talk. Basically, it is a different type of talk because related to innovations and patents, and for nominating my name to CSIR to deliver this talk. What I will do, I will be going through the patents and the related areas. In those areas, I would like to make a presentation. Therefore, the topic what I have to select is, it is innovations in advanced functional materials, under which all the work which was carried out. Of course, there are specific areas like nano areas and also smart materials. So coming to the next slide, these are the patents granted mostly, and 1 or 2 may be filed very recently, and they are basically falls under material science, and first 2-3 patents are on piezoelectric materials and devices, and there some 2-3 are there in nanofiber materials and applications. And earlier we have done some hydrothermal synthesis of ceramic materials and their applications. So therefore, the outline of the presentation, I will keep it with a brief introduction on type of materials. I will just go quickly to go ahead with in-house developed piezoelectric materials, and the PZT powder technology transfer was carried out to industry, and then fabrication of piezo devices, namely accelerometers, ML stack actuator sensors, polymer and ceramic nanofibers, their method of preparation and characterization and various applications, and novel synthesis of alpha alumina, which is widely used ceramic material. Alumina trihydrate is widely used also filler material, and then finally conclusion. Coming straighter to come to the transfer of PZT powder technology, this work was carried out, actually initiated under National Program on Smart Materials and PSM in the year 2002. The program was initiated by Dr. V.K. Atre, the scientific advisor to Raksha Mantri at the time, and the main issue was there to prepare the piezoelectric material is not widely available in the country, and whatever is available, that was there is a large variation in the piezo properties. Therefore, their usable for their application was restricted. The main aim was, I was told when this project was supported, that you have to develop basically a material which is having a high piezo property, which is measured by the D3, which is nothing but the amount of charges picocoulomb it generates with the force of 1 Newton, and also there should be minimum variation of the properties. As you can see from the graph, at that time in 2002, commercial samples are showing large variation in properties from 300 to 550 picocoulomb per Newton, while after NL we have prepared material, it was showing the minimum itself 500, and it is narrow band the properties are achieved. And I'll come the details, the presentation thereafter. But then it was in 2018 where this technology was transferred to a industry in Bangalore called MS IPA Private Limited for commercial sale of PZT powders, and there are different products. So what is that this technology all about, and where its application? Now coming to the company where IPA, the IPA is manufacturing or fabricating its indigenously IPA fabricated accelerometers, as you can see in this case. And inside this, if you see, it is contains PZT ring, and this is exactly the shape of the PZT ring which is there. And our contribution is the technology to prepare this PZT ring. This is just like a heart in a human. This one, it is very crucial because the accelerometer measures the vibration, the force, all that, and that is actually directly applied to this PZT, and this PZT generates the charges. PZT generates the charges, and that charges are basically proportional to the level of vibration, also level of the that is the material properties. And what has happened when we have characterized after initially 2 or 3 times we have given our samples, and then they have tested, and then some improvements are required. Then finally it was optimized. Hello? Is it audible? Please switch up the market. Okay. Now, then the output voltage was high in our case, particularly NL prepared. As you can see, for any acceleration, you will say the level of output in millivolt is much higher. In 20, what you say, about 1000 millivolts compared to the commercial PZT, what is generated about 600 to 700 millivolt. And moreover, the most important, the linear behavior of this output voltage at different acceleration. That's what made this decision by the company to go for our PZT powder technology. And what is about this? The technology is to prepare the PZT powder, which PZT is nothing but lead, zirconate, titanium lead oxide, ZrO2, titanium, and some dopants. So it is a multi-component material, and this comes out finally a uniform powder, and this is a very fine powder having particle size less than 1 micron, that is 0.7 micron. So finally, we have developed this material which is after sintering, we get about 98.5% density theoretical, and also it generates a picocoulomb. Charge is very high, 665 picocoulomb per Newton, and the dielectric constant and dissipation factor loss also very less. And what you can see, using this powder, you can make this PZT rings what you just developed, and this ring is prepared, and then at a different frequency they are tried, actually 500 Hz, 1 kilohertz and 5 kilohertz. In all the cases, you can see the NAL developed PZT was producing higher voltage, and also the graph is totally linear compared to the commercial grade PZT. So using this technology, once it's a technology transferred, of course it was just before the COVID, and however the company has gone ahead in establishing the facilities. As you can see, this is the facilities already available with the company. They have got roller mills, they have got the furnace for heat treatment of PZT powders, and also pellet tablet making machine, and they are making these powders, and you can see these are the green, and after sintering you get this PZT rings. And these PZT rings are also poured in this high voltage DC, and finally they fabricate PZT accelerometers. This is the final product. So the company is already producing these rings, and interestingly, this technology they have used actually for their own use actually, because they require these rings for their final products. In addition, recently they have also actually supplied some PZT powder to IIT Guwahati. So in this area, better, I thought I will also just throw up on some few slides. What is the technology? How it was difficult to know what is the effort it has gone, but with the less time, so I will go only for main slides. So maybe just this is the materials filtered. I will not take much. What I say that the materials also divided into metal, ceramics, and polymers and their composites. So all modern materials, you can put them in functional materials, where for any functional properties such as thermal or magnetic or electrical, all that it must have the properties depending on the applications. Similarly, nanomaterials having less than nanometers because of their high surface area to volume ratio and quantum effects, they are very promising materials. And smart materials, which PZT comes under smart materials. What they do is it is able to materials which can sense and actuate. Then only those materials called smart material. For example, a material PZT which can be used as a sensor, or that is to measure the vibration of a aircraft or aerostructure. So it can be used to make as a sensor, and at this with the control system, it can be also applied as an actuator to reduce the vibration. Therefore, these are the smart materials because it is able to sense the vibration and able to reduce also the vibration. Therefore, these materials are smart materials. So whatever I will be presenting on PZT, that is smart materials, and little bit on nanomaterials. So broadly, all the materials comes under functional materials. And this is typically the piezo word, Greek word, which is pressure and pressure electricity. The direct effect is in mechanical stress. When it is converting to electricals, it's called direct effect, and that is in sensor mode. And converse mode is electrical field you apply and you get the mechanical strain and the block force, which is used for the reducing the vibration. And typically in a house we use also to lighting a gas stove. It contains a PZT material. When you apply a stress, throw a finger, and then it generates some charges, and that helps in the lighting. And you can see the direct effect in this case. When you apply the pressure, there is a voltage is generating, and similarly when you apply a voltage or electric field, you get actually a actuation that is motion in this case, and also block force also can be generated instead of displacement. So this concept is used to make smart structures, aerospace structures, and that's why this is interesting for NAL. So the PZT can be used as a sensor, actuator with the control system. We can control the vibration in different places of the aircraft. So the vibration level can be minimized. Basically, PZT is a perovskite structure of AbO3 structure, and the lead and oxygen, which are bigger, there lead is at the corner and oxygen at face centered position. However, zirconium, titanium, which is very small because of it is tetravalent cations, it is there in the center. It is a place to move up or down depending upon the electric field what you apply. That's called polling voltage. And normally in an unpoled condition, the electric dipoles are arranged in a random oriented, like magnetic analogy to magnetic things. After polling, they will be aligned in one particular direction, and after polling also this will remain. Now, if somebody wants to attempt PZT material to synthesize, one is to go for this phase diagram. What is interesting, it is a solid solution of lead zirconate and lead titanate, And at this composition, about 48-52 or 52-48, so both sides, tetragonal and rhombohedral, coexist phases, and in this case, both tetragonal and rhombohedral case exists. Therefore, this is called morphotropic phase boundary, and one is to synthesize in this condition, and so, and further addition of the dopants, it will also enhance the properties. In our case, you have to go for the soft dopants, wherein in ABO3 structure, you have to select a cation of a higher valent, one valence higher, so that we create cation valency. And this cation vacancies that will help also easy domain wall motion. So this is the science behind little bit on piezoelectric material. And when you take various precursors and you have to do by wet chemical method, this is a very important. We should not go for the mixed oxide chemical method will help in homogeneity in mixing when you are dealing with multiple number of components, multi-component systems, and their calcination. Some are 1100 plus and de-agglomeration after cooling, and you have to granulation and compaction to make some pellets, and after their sintering we have to make polishing and pooling and characterization. This is the method for which piezoelectric materials, and one should not forget to try different compositions near morphotropic phase boundary to find the existence of both tetragonal and rhombohedral phases to make sure that that is the right condition, right kind of the material what you have to select to get the maximum piezoelectric properties. And after that, dopant has to be added so much. So I will directly skip actually finally. So in the first project, we have developed the large scale 150 gram batch piezoelectric material, which was having about nearly 600 picocoulomb per Newton, and then it was further upscaled up to 1 kg batch in a CSIR 5-year plan project, and then further 10 kg per batch. So to upscale 550, which is still having high D33 properties, and as you can see the particle size, it is having less than 1 micron size. That shows it's a very highly, very fine powders. Therefore, there is a reactivity is very good when you make the bulk materials or for a sintering. So what is that interesting in that? What is the innovative steps for enhancement of piezoelectric property? It is a very difficult actually to get into piezoelectric material when you prepare a high picocoulomb per Newton or high piezo properties. Generally, papers will be dealing with on studies on dielectric and various other properties, but there will be hardly few papers which will give you actually to suggest for high piezo properties. And even if you try them, it is very difficult to get the properties. I don't know, people leave also some amount of gaps in those properties. So this has to be learned actually ourselves. And if you have to take a random PZT composition, you may end up with just 50 picocoulomb per Newton. But if you follow morphotropic phase boundary, what I have shown, so that will take you up to 200 picocoulomb per Newton. But then in MPV, you have to add some dopants if you will be able to enhance further 350 per picocoulomb per Newton. And if you optimize the dopant addition and the dopant type of dopant and overall composition, it may go beyond 550 picocoulomb per Newton, and that has happened in our case. So from our experience, I am telling that at different stages of its development. And finally, optimization of overall composition and process optimization has led finally got the maximum value of 712 picocoulomb per Newton. And this is the final composition which we are finally having. And this composition, final composition was the transport as the technology. So this is about the projects. So what we have done is from NPSM, CSIR 5-year plan project, again second phase of NPSM, again CSIR 5-year plan project, and there was a project from Electronics and Information Technology Ministry, and that was for energy harvesting. So 4 or 5 projects we have carried out over more than a decade, and there is a technology transfer, and one PhD student also, as one student has got PhD in this area. So there are several papers and book chapters was there. Now coming to the next one, after developing PZT, the PZT is basically contains lead oxide, which is poisonous. And in Europe and USA, the lead oxide is not lead bearing compounds, even they are not allowed nowadays. And so therefore, the scientists have shifted towards lead-free piezo materials and devices. Similarly, NL also, we have also initiated after PhD this lead-free piezo materials. A student joined for PhD program and he carried out initial experiments. We have selected BZT, barium zirconate titanate, due to certain advantage due to shortage time. I will not get into details, with certain dopants, and initially got about D33 of 330 picocoulomb per Newton. And there are some composition studies. So I'm just giving one slide out of his PhD thesis, and there are several publications, and patent was also filed in this area. Then afterwards, recently we have enhanced the property further up to 510 picocoulomb per Newton, very similar to PZT what you have developed somewhere in initially years there. And here further we have fine-tuned the heat treatment process and dopants, and therefore, as you can say, zirconium titanium ratio are also changed, and therefore we have got hysteresis different, and also it is also published recently. What is interesting, this was also tested for accelerometer, and it is also showing the same linear behavior similar to PZT. That means the lead-free piezo also we have now developed as a technology which can be used for the accelerometer applications. And in fact, this is now included in the Mission More project which is going on currently along with Sri Pilani, and that will be on LTCC based accelerometer development. There was a project also sanctioned in this lead-free piezo materials from Naval Research Board during 15 to 18. We have filed a patent, and also two students. One student I already received his PhD degree, and also the other one is now continuing under ACSI. Mr. Tejas, he is enrolled in ACSI, maybe completing at the end of this year. So there are several publications at the. Fortunately, we have contributed one review article at the beginning of this when PZT was getting over, and then at the beginning years of the lead-free piezo materials. So that's why it was very popular, and it has got the citation of 970 so far in the last about 14-15 years. So there are also book charters and other publications. We had also Indo-Russia collaboration and Indo-CSIR BMBF, which is again a Indo-German project that was also completed in this area. Then coming to fabrication of multi-rate stacks. Now, what I have explained so far is the development of basic powders, PZT and PMN. But then we have to make them devices in the form of multi-rate stacks. And this was initial years which were prepared up by cut and bond method by crude way. And as you can see that we have done multi-layered stacks here. Mainly multi-layered is required to reduce the voltage requirement. So driving voltage can be reduced to up to less than 150 or less than 200 volts, so that they can be put in an aircraft with the available voltage. Otherwise, they require transformers, which is an additional weight that cannot be entertained in an aircraft, because weight reduction is always a primary requirement. When this was developed and there was brainstorming discussion, that we have to further reduce, because this was requiring also 650 volt. Then we calculated that we have to come down each layer of 100 micron thickness. So we have to get a tape casting unit, screen printer, precision, all these units. It was purchased from Slovenia under 5-year plan project. And as you can see, this is a photograph piece, typically PZT tape. And using that, we have developed, these are amplified actuators and various other multi-layered stacks. And typically what you can see here, there are 120 layers, each layer is 100 micron, and weight is 9.4 gram, and area is 12 mm by 11 mm, which is 132 mm square. It gives a block force of 5,200 Newton force, and also a displacement of 10 to 12 micron. So this is also published, this one, and this was used actually in the airband for the that is for a dynamic characterization, to prove that this our API, what was developed in-house, it is working for the that is reduction of the vibration, and that was carried out to different voltage and different frequency, and it was found that the applied of applied waveform and the output, whatever comes out from API is of very similar nature. Therefore, they can be put in cancellation mode, and this was proved in NR. So there are some projects on energy harvesting, and I'm not going for the slides on energy harvesting. Now, that is about the smart materials. I'll come now to the nanomaterials very quickly. And again, this was carried out, the preparation of polymer and ceramic nanofibers by electrospinning technique. Fortunately, in 2005 and 6, I had been to NUS Singapore under CSIR Raman Research Fellow Scheme. And as you can see, the nanofiber to define the L/D ratio, that is length to diameter ratio, has to be more than 1000, and its characteristics, that is the diameter should be less than 100 nanometer. And by using this facility, we have prepared initially, this is the first publication with Professor Ramakrishna, who is from NUS professor, and we have prepared alumina nanofibers. Then after coming here, we have got this facility now, electrospinning unit, and we have got a multiple electrospinning unit to prepare our membranes for various applications. What is interesting here is that because of nanofibrous nature, it is having a high surface area to volume ratio and very good for various sensoric applications. Now, our initial years actually was to prepare also not only polymer nanofibers, but to go for ceramic nanofibers, even piezoelectric ceramic nanofibers. So we have successfully prepared barium titanate nanofibers by electrospinning, and as you can, this is there in Ceramic International published. I'll not get into details. You have to take the precursors of barium titanate and take the PVP as the polymer vehicle and do electrospinning so that you generate the fibers, and after heat treatment, you will get the nanofibers of barium titanate. Now, this will help in making very thin sheets of dielectric materials, which are, when we are looking for the miniaturization of various components, so we require also very thin things. It is not possible to make a big bulk and then cut this brittle ceramic materials into very thin slides of few microns. The best thing is to approach to make by this electrospinning and make very thin sheets. Similarly, this is a lead-free piezo nanofibers. This was also filed a patent, and this was a very thin nanofibers of BCZST nanofibers, and this is also published. And what you could see that D33 have got also about nearly 400 picocoulomb per Newton, and it has got a characteristics hysteresis loop. So this was also published. Similarly, this Samaria nanofiber was prepared by electrospinning technique, and this was also filed patent. The publication is now in Ceramic International, similar procedure. By only you have changed the various polymer precursors, and also processing conditions accordingly you have to change various concentrations, and their diameter was measured. Their diameter after calcination was also measured. So all those details are available in the published literature also. Similarly, this was manganese tetroxide was also published electrospinning technique, and this is also now finds in the publication. And when this pandemic came, we thought of use this electrospinning technique and prepare PAN nanofibers that mainly for filtration of materials. In fact, we had tried earlier with water technology, that is from DST1 project was sanctioned to make this PAN nanofibers. And what you can see, this PAN nanofibers of 100 micron thickness were tested for microbiological reduction test in Eureka Force R&D Center, Bangalore. And what you could see in this case, it is completely removes E. coli bacteria at the tune of 99.9998% of E. coli bacteria. So this was also published, this one. And the same thing was extended to make this face mask. And this is also tested in Citra, Coimbatore, which also complete reduction, more than 99.9% reduction of aerosols, suitable for N95 grade face mask. And also there are other tests on blood and other things of various tests, and that is there. And this project, a project proposal was also submitted to DST under Indo-Portugal, and the project is also sanctioned to take forward this work. So DST, we got this project from 2015 to 18 under Water Technology Initiative, WTI. So development of nanofiber membrane for reduction of emissions of microbial for purification of water. In this case, 2 patents are filed, basically on piezoelectric and ceramic oxide nanofibrous materials. One PhD student is just in 2022 completed, that is preparation and characterization of polymer nanofiber membranes by electrospinning for filtration application. He basically tried both water and air filtration. And recently, last month, the other student has also got in electrospun polymer nanofiber for various applications. And it is basically varied, that is surface wettability, and it has a lot of applications, including biotechnology applications. Now, this is about there are a lot of publications in this electrospinning area, which we continued with the 2 students and PhD students and few MTech students, and we are continuously working on this one. Then coming to synthesis of high purity ceramic oxide, this will come to the work which was carried out before 2000 at the beginning of my years in NIL. So one such was there. I have interacted with NALCO, National Aluminium Company, that is in Bhubaneswar, and they said that ATH is a promising material. They had given a sample, and what was interesting, we thought, okay, ATH is very easy to prepare, but what was required is when you prepare, you precipitate the ATH, you get the aluminum trihydrate, whether any aluminum salts at the chloride and with ammonia you will get. But what was required from that? It is a bright white and low apparent density, 0.24 to 0.5 gram per cc, and most importantly that it should be insoluble grade, so that it can be used as a also as a fire retardant materials and as a filler in paper, plastic, rubber, and also antacids, various applications. And finally, patent filed and technology as a transferred to a company, Mysuru Minerals Private Limited, for commercialization. And the product is a bright white ATH self-seeding. There is an innovative in this thing because it was done by a process of self-seeding, and the byproduct is a hydrogen gas. Now I am realizing the hydrogen is very important in recent years. So whether this process really not only to generate ATH, but also this is a fantastic process to generate hydrogen gas. It's a reaction of alkali with metals, and which generates a pure form of ATH. And this was a very cyclic process, and this is a very interesting this one there. It is very quite in that it looks very simple once it will be explained, but there is a highly tricky thing. It was there, and we have done it, and we have transferred the technology. And the technology transfer, this was came also in CSIR the magazine, that low density aluminum trihydrate is developed at that time. And this is one more interesting area which we are having actually hydrothermal reactor in NAL, which is fabricated in-house, so by our engineering services section. The good thing here is that it's unlike commercially available. Here you don't have to apply the pressure from outside. It is the pressure is autogenous. That means when you have a fluid or water inside, it is in a closed chamber. After we put the liquid and reactant, say metals or some other salts, and we cover it with gasket, and we close that and we heat it. Then water is finally is heated to high temperature, and it will generate a high pressure. So pressure is autogenous, though no external pressure is generated and no applied, and so there is no cost. It is only moderate. It's just like our pressure cooker use for to have quick for preparation of the food. Similarly, in this case, what went well in this case is that is fantastic, which the alpha alumina is widely used. It's a very among all ceramic industry, in all ceramics, alpha alumina may be used in about 30–40%. But even if you prepare the high purity, that is which produces alcoa, they go by a process called Sol-Gel process. So you will precipitate aluminum hydrate, and then you have to heat it at a high temperature to the tune of 14 to 1600, 1700 degree, finally to get alpha alumina. And in the process, it will be also preparing, or it will be transforming into theta, eta, zeta, gamma, like a transition, number of transition aluminans. So finally, you may not get a highly pure form of alpha. But this process was actually generating alpha aluminate of 500 to 550 degrees centigrade in compared to 1600 temperature is required, but there is a pressure element is there. So about 30 to 40 MPa, which is not applied from outside, but it is autogenous. Therefore, it was very interesting to generate, and we filed some 2-3 patents in this area, those area, and even this was also communicated. And what is interesting here from the reaction is that initially it reacts with a metal and it forms a boehmite, and that boehmite is having water molecule, and that it releases straightforward without getting into transition alumina, it forms alpha alumina. Later on, this was changed actually. I collected some sample from NALCO and we have tried their alumina trihydrate, which is prepared out of the bauxite to make it much cheaper, and that also has worked. And after that, we have communicated to NALCO, and at that time, the DGM has also expressed, has mentioned, I am very happy to note that you have succeeded in converting hydrate into alpha alumina at 450 to 5 degrees centigrade, which is something very unique. But however, after that, the person I think got transferred, and then we are not able to have a continuity to technology transfer. But this technology, I still feel it is very interesting. The only thing is that there is an initial investment cost maybe on the hydrothermal reactor, but that is also done in a number of ways recently using various methods. So at that time, 2-3 patents we have generated in this area. So there are some patents as we can say, and the know-how technology has transferred, that is for the ATH. So these are the publications which is generated out of it. So from my experience, I can say that development of materials provides opportunity for innovation, because material science is very interesting. Anything you try do with little bit of inputs, and you will find that something new comes out. It is highly interesting. So always it is innovative. One can be really be very innovative in this area. Material science provides that opportunity. And all high performance requires materials requirement day by day, stringent materials required for various applications. That is possible through innovation. These are the only few innovations or innovative ideas or the examples I had given. Even currently, we are also using some of the processes to get into hydrogen technology, into hydrogen valley. So I will not go into details of that. That is still, we have got something, and that is under patenting. So I think with this, I have come to the conclusion with the acknowledgements from my colleagues, those who are working in my team. This is my own team, not as a division as a whole. It is a own team, and there are students, about 5 students. 4 students have got their PhD, and 7-8 students about MTech thesis they have prepared. I'd like to thank Director NL and so many directors, the last 3-4 directors during through which I have able to carry out this work, and including the current director who is nominated my name to make this presentation. Various funding agencies, NPSM, NPMARS, DRDO, METUI, DST, Naval Board of ARDB. So all those programs actually helped us to generate the funds to carry out this work. CSIR 5-year plan programs, 2-3 programs, and CSIR ICU for arranging and coordinating this program to make this presentation. Thank you very much. So over to you to IPU.
Yeah, thank you, Dr. Panda, for a very illustrious and very well-defined presentation and talk on advanced functional materials. I note that you have not only worked on piezoceramic materials, which can be used for sensors and actuators, but you have also worked on materials which can be in the form of nanofiber membranes, which can be developed into membranes. And of course, the last thing that you talked about, the alumina trihydrate, which is used for fillers and can be used as a fire retardant materials with quite a few applications. and which has a potential of byproduct, which can be hydrogen can be a byproduct and which can be scaled up. This process also, because of hydrogen being used for alternate fuel right now, and it is an energy efficient program. So I hope all the best for you. What I wanted to ask you about, one question I'll ask first, and then we will take question answers from the audience. Very simple questions. We say piezoceramic materials and we say piezoelectric devices or materials. So are they or are they not similar? Just a very simple question from a person who is not from material sciences, but from a biotechnology background. I'll ask you a very simple questions that how are they similar and how are they not similar?
Yeah, this piezoelectric materials is the basic material, that is basic powder which is required, and piezoelectric device is to use this material or the powder to make the devices. So one is the device which will be directly going for application, and the other one is the powder. The powder will have you have to play with chemistry and physics so to generate this basic material. So these are the two different things. So our thrust was to enhance the you have to develop a basic material which is required for a high piezoelectric property, and the variation of the property has to be minimum so that it can be used. Because if you have one property 600 picocoulomb and the next material will have 300 picocoulomb, that the same that graphs whatever you use for the various calibration cannot be applied. And our effort was there to have a very high piezo properties. We have taken up to 600 plus picocoulomb per Newton. Is very unique. Actually, I don't see much papers on those. And similarly, not only that, we maintain more than 550 to 600 picocoulomb minimum, which the commercial grade generally was used to have 300 to 600. This one there. Well, I think you have said, madam, that your background is biotechnology. So just to tell this nanofibrous materials, the last student, the Soumya was there. She tried actually for adhesion and anti-adhesion properties of using this material. So she tried.
You said that because they were antibacterial properties. They were having antibacterial.
Yeah, E. coli bacteria, that is one thing. But recently, fortunately, she came with a little bit of biotechnology background. And I said, okay, we will go for varied actually wettability study. So,
somehow.
So we tried actually modified nanofibers.
People to please please do not speak in the presentation.
One after other.
Yeah, you can go ahead. Yeah, yes, somebody from CSIO was speaking, I think.
Yeah.
So another thing was that we can use these in circuits and semiconductors. These kind of materials, the piezo ceramic materials, can be used in the semiconductors. And are they the same which has been developed from your laboratories, or they are only for the vibration testing and for aircraft related matters?
These are actually for aerospace and defense. For example, all sonar transducers in naval ships, either to measure the depth of the ship or to send a signal.
So they are not same as for used for the semiconductor.
They are used for energy harvesting. They are used for measure of force, vibration. Okay, and now they are used actually in high-end cars like BMW cars for fuel injector. Okay, systems. So what it generates, its opening and closing can be made very precision, and therefore the amount of fuel required that can be passed by through these piezoelectric materials can be done very excellent, so that extra fuel it will not go and that will not generate pollution. So in BMW cars this is applied, so that is called fuel injector system. These things are also used in aerospace propulsion system like NASA, and we have also developed one ring-shaped actuator. Because of the time I have not included that. Also we have tried with the ISRO. Okay, some few trials are there. So very precision opening and closing of valves wherever required. This can be used and it will compete better than the solenoid based which are very heavy and which may get affected in the presence of magnetic field. But here the material what is required a very small, only few grams, and also it is not affected by magnetic fields. So that is the specialty. There are a lot of applications of this high-end engineering materials. It can be used as a various applications. But
yes, of course. I will give the mic to my colleague, Dr. Lipika. She will take the question answered from the audience now. Thank you.
Thank you very much, sir, for this very informative talk on functional materials, and particularly piezoelectric material, lead-free piezoelectric material, PAN nanofibers, and samarium oxide nanofibers, and their properties and how they are being used in different fields. So we'll be taking the question answer session. There are some questions, I think, in the chat box, and we also request the participants to raise your hands so that in case you are called, you please introduce yourself and you can ask your question. So we are taking question from the chat box now. The first question is, what is the present status real-time data of smart material research and development in India?
Regarding smart materials research, I think it was again in 2000-2002 when a 75 crore worth project was put together under National Program on Smart Materials, which is led by, as I told, Dr. V.K. Atre, the scientific advisor, Raksha Mantri, and that was operated from ARA. And there are some parks were formed, project advisory, some, and this one appraisal, this one park, and they are also run from IIC. And at that time, what was interesting, what was done was that all these basic materials was tried, identified. PZT is just one. So the other materials is safe memory alloys in metals. Okay, so that is one more smart materials. Then we have PVDF, which is a piezo polymer. Is a polymer of pivot. So that is also this. All these three things have started in our material science division. So we got simultaneously. These are the projects. There are other things are there. Magnetorheological fluids, optical fibers, all that. So basic material is developed at that time, and there are a lot of fundings were given across the country, and also thereafter the devices also focused in their second this one. The level, that is second phase, that is NPMAS. And in fact, today we have got Institute of Smart Structures and Systems, ISSS. One can go through the websites and will get a lot of information which is there from IISc. And IISc, there is also a journal also there on ISSS that is published in every month. And this is really that is interdisciplinary area involving electronics, mechanical engineering, mechatronics, materials, all that things. So I think one can get a lot of information at the current status from ISSS journals and ISSS society. In a very short time, it's very difficult to get. But what I can say today, basic materials are there, basic devices are there, but never ending, because devices are required of different types for various applications, very complicated technology. One can only contribute to his own area, but here it is a requirement of highly interdisciplinary things, and all those research are published in ISSS. It's very interesting. I would like those who are interested, or those who are working, or those who are looking for some smart devices, they should go through this ISSS and the its proceedings, which is published every month. I hope it answers.
We have a hand raised from our ma'am, Dr. Vibha Malhotra. Ma'am, please.
I think before me there's another person, Dr.
Yeah, Dr. Nagaya.
Komu Nagaya. So please, Dr. Komu Nagaya, please do ask your question, and then I'll ask.
Madam, is our professor presented a very nice, excellent application oriented topic in the today presentation. We are actually saluting to our professor. But the most important thing, maybe CSR laboratories or the Indian companies or whoever it may be, there is any state-of-art facilities, especially for this maybe age prouders or a smart materials, whatever the presented today, our professor. So what is the exact status that society want, which companies are doing, or which CSR laboratories is doing, and what is the technology available for the benefit of the companies or the society? That is my question.
Yeah, just to answer actually, before some time, I think just to give you example, before 2-3 months, 3 professors came from IIT Guwahati. So to NIL, because one of our scientists from structures division went for a conference. They are looking very badly for PZT. They are saying we are not getting this material, and they came to know that NIL can help. And they came and they asked me. So then I have directed to today the PZT powder and the devices are available with a company called IPA Limited. It is in Pinia, and they have the website. One can search and they can get the devices and the basic raw material from there. So before few years it was not available. Now these sort of materials are all available in the country, but not by many. So at least in Bangalore, this material is now available. And if somebody wants some specific customized devices, that may be possible in our R&D in NIL itself. We may be able to fabricate and give you. If it is not possible, if it is more numbers, we will direct to the company and they will do. Recently, we did same thing with ISRO. So on accelerometer things, and we had visited them and we have asked the company to fabricate and prepare. So it depends upon what is the requirement, because these are the very specific applications. The devices are higher end and these are smart devices. As I told, it's not a common materials. So, but nowadays it is available in the country, and industries, we have transferred the technology. Either the industry will fabricate or in NIL laboratory will fabricate. So whoever requires, we are welcome. I think email is I have said.
Hello, my intention is here. Why the IITs? Why the IITs in the country? Why they are not concentrating on especially for one particular area? Because this is most important instead of doing from the project. Why not you do the
Dr. Nagaya,
the professors are not giving this type of the proposed project dissertation to the IITs. So what is the status of IICT, especially for the smart materials?
Yeah, to answer, we should not comment on IIT, of course, but I will tell you, I will give you the clarification. IITs are concentrating, they are using specific devices, and they are going for a lot of basic research and generating a lot of data or the equations, algorithms, all those things. So fortunately, it is our laboratory CSIR, so we should take pride that we have developed this basic material. So I think we would have supplied a lot of materials to IITs. So it is a good thing for us. So now, because this program was initiated in 2002, now today we are having this technology, whether it is IIC or even IIC. In IIC, we are supplying a lot of it to aerospace department, mechanical engineering department. Even whoever comes, we are giving even samples to them. So let us not worry. They are doing their job. They are academic institutions. They are guiding their also students, and we have developed our technology. We are transferred. So that is our job, and it is fulfilling that for quite some time we have spent a lot of time here. But I was thinking, unless it is transferred, it will again, I retired, it will die down technology. But it has happened that before I retired, this technology is done, now it is available.
So finally, what I want to say, in the CSIR who are taking the staff, they have to continue your research. Then only will get the cutting edge technology. Otherwise, it is closing on your retirement. So that is my intention asking this question. Thank you very much. Thank you very much.
It will continue. We have got the group. We have got the group to take forward. Even as I told you, that I'm not going for the details using various nanofiber technology. We are even going for the hydrogen technology. Even a review article came. One can search actually from my Google this one on various novel way to go for the next level of we are also trying this route finally to go for the solid oxide or solid state batteries, our thrust area, and also hydrogen. These are the two main areas which I feel that we will initiate before I lay down office.
Thank you very much. Thank you very much. Thank you very much.
Thank you. Thank you. Thank you.
Dr. Nagaya, you can identify your affiliation. Where are you from? Dr. Nagaya?
He should have, yeah. From which lab you have?
You're
Hello,
He's
from?
identified.
Sorry. Which
He's
lab are you from?
He's
Anyway.
from IICT, I think. We had him. He's Dr. Nagaya is from IICT. He is in TKDL part of. He's heading the TKDL division of, I think, IICT. If he can say that.
No.
Yeah.
The
You are not that?
I will tell that inconvenient truth to the rest of the world, but nobody is inviting to me that what is going on.
So, Dr. Nagaya, let's not talk about what is going on
No,
anywhere else.
Inviting to me. That is a problem.
Okay. Okay. So, no, because you are being seen here as a meeting guest, so I was wondering. And I think, Dr. Panda, I must appreciate the passion with which you presented your innovation and, you know, what innovative steps you've taken and the way you brought the industry also. And maybe created the enough base for Indian industry to come up, you know, with this material. And as you said, there are many applications. In fact, this is in fact, your group, I'm sure, is doing commendable work, even not only in the space of aerospace, but also other related things. So thank you very much. In fact, that's what I wanted to, you know, I thought that this is not really coming out. You've shown your journey and everything, the kind of roadmap that you followed. So, you know, creating an industry on its own within the country and to make available this material, that is what is really needed here. So thank you very much.
Thank you very much.
Any more questions? Anyone?
Yes, there is another question from Dr. Suguna Lakshmi. The question is, can we use our aluminum trihydrate as nano emulsion for making fire retardant textiles? And there is another question. What about the idea of using nano ceramide based filter for flexible fabrics?
Okay, it can be used as a filler. This is meant for that. It was meant for various applications. In fact, for paint industries as a filler, for paper industry to give the white and also low weight. The papers must weight low, so that's why it's that is density, apparent density was kept at 0.24 gram per cc. So it can be used for fire retardant, because what it is happening that it can take a lot of that is heat energy, and that heat energy will be utilized in ultimately it will lose the water molecule, so it can absorb a lot of heat energy, and that's why this is used. So her question, if it is towards fire retardant, yes, this is widely used for that. It's used for also antacids. So it is various medicinal things as a pigments for various things. It is used for the synthetic marbles. It is used. So the whiteness, actually you get that synthetic marble, and also it keeps the weight also less. So there are a lot of applications. That's why this was taken up, and this problem came from the industry. In fact, I was not very happy that my alumina technology was not able to transport at that time, because as junior scientists we did have much scope here. Nobody will believe that in NAL alumina is producing. It should have done in CGCRI or elsewhere. So there is no connection. But I still feel that alumina technology is a very interesting. I was thinking sometimes that how that has to be transported, because that is a lot of. It produces at 450 to 500 degrees centigrade, which is done actually very high temperature. Of course, there is the initial cost also there on the making the hydrothermal reactor, but that can be fabricated enough or by good mechanical engineers nowadays available. We don't have to take costly. And as far as Dr. Suguna's question is concerned, yes, it can be used for the highly retardant and various other applications. And moreover, this can be used also to preparation of alpha alumina, because it has got alumina trihydrate 3H2O, so that water molecule, once it goes, it will generate also alumina. So it is a lot of applications in this.
There is already one request from AMPRI, Dr. R.K. Bharlia. Can it be possible to join together for applied research in nano FG lead functional material? So it will be. So
Yeah,
maybe both of you can connect offline and discuss this further.
I think this is the specialty of these lectures. I must thank our CSIR, your division, your unit rather, IPU, for bringing scientists in one family through this actually. You see, AMPRI is working on materials. We are working also here materials, and there are many materials laboratories are there. We are working in different cells, we don't know each other perhaps. But after this, people will know if CSIO is working something on piezoelectric for their development of some sort of scientific equipment. Even CRIPLN we got like that way. So now we have joined together. So we can work also networking as possible through various mechanisms and various projects, which is also by in-house CSIR also funds. So we are welcome from AMPRI, and not only from AMPRI, from any other laboratory, any other our CSIR laboratory. Whoever finds that some application and would like to join, we are most welcome. One can go through the details of published literature nowadays available in Google Scholar or through ResearchGate, or one can communicate, and then we will find various areas. And not only this is only my specific group I am telling. If you come to the division, there will be so many areas you can work. In NIL as a broad, you will be able to get many. So it is a question of visiting once to NIL, or initially coordinating with through the emails and or maybe even video conferencing with different laboratories after the CSIR as a whole, and then finding different areas where we can work together. This will be tremendous scope of putting a lot of interdisciplinary expertises together and to generate very novel materials. Material science really offers people, those who bless, those who work in material science. It's a really challenging area.
So there is another question. I think hand raised. Dr. Tiwari, please.
It is me.
Yes, sir.
I'm Dr. Tiwari. Yeah. So congratulations, Dr. Panda. It was very nice presentation. I was listening to your comments on this flame retardant fiber, ceramic fibers. So maybe it is flame resistant or flame retardant, because we have studied flame retardant. It's something you add which creates some kind of cloud which prevents oxygen penetrating inside and then burning, allowing more burning to happen. Whereas flame resistant is something which you are referring to. So I think this is something which is you have to consider. Second thing is, I am also working, actually, you can say, on these nanofibers. And I am aware of one startup, which is very good startup in IIT Kanpur. You might be aware of. They have developed this SWAS nanofiber for this during corona outbreak. What they have done is not only fibers, because many people are making nanofibers, but commercializing, making them on large scale is a problem. And for that, they have developed a machine. So are you thinking, because you are working a lot on nanofibers, can you develop a machine which can produce these nanofibers? Because there are different type of nanofibers which are coming for different applications. If that is possible, then it will serve the country, and that will be a very good development from your side. Thank you.
Regarding nanofiber preparation, now commercial grade is available in the country, and particularly from IIT Kanpur, Chemical Engineering Department PhD.
But they are not sharing. They are not sharing their technology. They are doing it by themselves.
we are having a unit now where we are having multiple electrospinning. That is 10 heads at a time. So what happens? There are 10 heads in which each one you will have the syringe with the polymer material, and each one will be preparing nanofiber on a belt conveyor. You will collect them and you can get a good amount. You are preparing a good amount which will be in few meters together. So these things are nowadays available even in our country, and maybe details if you want we can give. So that is available, and
so that is techno-economical. You can produce and you can also sell at commercial level.
Exactly. Fortunately, a few years before, it is only getting a electrospinning unit itself was difficult. You have to depend from abroad, you have to get it. But now in the country also it is available, and fortunately that way there. And there are some units are already there in Gujarat where they have put up textile industry, some where government R&D, whether it's Gujarat or
I am
government.
aware there was a machine
So
which was coming from. There was a machine which was coming from Czechoslovakia, which is installed in DRDO and somewhere in Ahmedabad, one lab, which was my previous lab, but that was very costly. It was costing around 3-4 crores.
No, it is just we got in 8-9 lakhs rupees, and the first one we got about 5-6 lakhs.
I am talking about commercial scale.
I'm telling, see, the first unit got from 5 to 6 lakhs from IIT Madras Physics Department. I forgot the Professor Subramaniam or somebody. And thereafter from IIT Kanpur, this is single, this one electrospinning. Now you have got 10 actually 10 multiple electrospinning unit, and we have got also fitted so that we can make electrospinning instead of zigzag formation, we can make them alignment of the nanofibers. Okay, so those things are applied, some alignments. Those facilities also we have got. We are trying also to make hollow nanofibers. So, but that will be, we have to look for some other to prepare the very hollow nanofibers. They are mainly used for drug deliveries, but that is a next level of work. So, but these are the plans actually. But we are having two different types of unit. One is a single electrospinning head, and the other one is a multiple electrospinning having 10 heads. So when you require more to prepare membranes, so we go for that one. When you have to do a research, a new composition, new things, we use mainly the students use only the single electrospinning head. So we have got both.
Okay, thank you.
We got both. Thanks to DST, who has supported water technology initiative, and under that we have procured that unit. So
thank you.
Thank you very much.
In the chat box, Dr. Suguna Lakshmi from CLRI Polymer Group has expressed that she is interested to join you, sir, in your activity.
In fact, just for information, Dr. Suguna Lakshmi was there in NIL before. She is transferred to CLRI long time before. I think she remembers this one. So she was in our polymer group, maybe 20 years plus before. So I remember the name, and I'm able to recollect her. So we are very happy to do any collaboration, no problem with CLRI.
Any further questions? Please raise your hands.
Tiwari, Dr. Tiwari, may please put down your hand if you have, yeah.
In case there are no questions, we have a question here. Like, sir, you have in your presentation, you informed that IPA Limited, you have transferred a technology to IPA Limited for that piezoelectric material and thing. And I'd like to know that how IP protection, you have got a patent or got a patent filed in that particular field. How IP protection has helped you in that technology transfer?
Yeah, here little bit of problem is PZT was discovered in 1880. Okay, and there are so perhaps NL we started towards the end of the PZT technology, but we have made it innovative, but we are not able to take a IP at that time. So we have taken IP, I mean the patent on the lead-free piezo. So the PZT technologies, the device when they have interested, so the know-how was transferred. That was. So that is not IP protected, I must say. Okay. So, but sometimes you take a patent and you are not able to transfer the technology. And if sometimes you develop something, it is a industry comes, you say, no, I require this one. Okay, maybe you could have gone for filing by changing. Always it's possible to file, putting some innovative things, but that was missed out. It was they came in a very short span of 1-2 months. They decided to go ahead. They came to know about our materials, and then some 2-3 times we have exchanged the samples and their characterization were gone. So that is actually not, we are not taken patent. So, but the technology was transferred. I was told transferring the technology is not a problem. So that exactly that part is not taken.
Again, subsequent technologies of alumina trihydrate and nanofiber membrane, you have patented them.
Yeah,
you have patented them. You have been able. Yeah, and you have been. Yeah, and maybe that patented technology. Did you think that it was a good negotiating factor while transfer of technology, or was it just that the industry wanted that, or you had done it and you had transferred it after patenting it?
Yeah.
How do you think that has affected that?
Yeah, what has happened? This was actually somewhere maybe 1999 or maybe 23-24 years before. At that time, we are not having separate cell for business development as such. But there was an opportunity came. Karnataka state has arranged a NAL industry meet. So we have a NAL industry meet, and I had 2 technology at that time I presented. So one is alumina technology and this ATH technology. And Karnataka state government has given incentive to the company to, in terms of maybe land and some also maybe various incentives. I will not able to know that. I remember a little bit that they got incentives, and they are all invited, their officers from Karnataka state government, and we made a presentation, and after that our laboratory has taken initiative in identify what are the areas they are interested, and they said this area would like to go for the technology, and that's where it was transferred. So whatever was negotiated, all that thing, I didn't have much this one, it was done. But maybe we are having a better structure placed as far as business development is concerned. Last 4-5 years, I must say, NL has got a very good business development group, BTG group. And really, we don't have to do much on this one. Sometimes we identify a serious customer who will take and we will put it, and there are a lot of, they take care of a lot of things, which was not earlier. It was totally, we have to develop the technology, you have to find the person who will take and all that thing. So sometimes, so now it is quite methods, and therefore NL is able to transfer a lot of technology in recent years. Yeah, I don't know whether you have got all the details. You will see last 4-5 years, NL has transferred a lot of know-how, and this one provided because of this group, which is always there to work on that. So the negotiations are done as per the CSIR norms, and it's fine.
Thank you very much, sir. As there are no further questions, I'd like to request my colleague Ajayta to offer the vote of thanks.
Good afternoon, everyone. On behalf of IPU, I would like to extend my heartfelt thanks to our DG, Dr. N. Kalaiselvi ma'am, for providing her immense support to hold this webinar series. We are really thankful to you, ma'am. Our sincere thanks to the NEL Director, Dr. Abhay Anand Pashilkar sir, for nominating Dr. P.K. Panda for this program. We express our sincere thanks to Head IPU, Dr. Vibha Malhotra Sahane ma'am, for constantly inspiring and supporting us for organizing such programs. Thank you so much, ma'am. On behalf of CSIR family, I extend a hearty vote of thanks to our family member and guest of the day, Dr. P.K. Panda sir, for sharing his research experience in material sciences. Your journey and experience will definitely inspire all the participants in this webinar. Learning is always a good opportunity to feed our mind as it helps us to grow. Through such informative webinar, we get a chance to boost our knowledge in the field of subject that might be unfamiliar to all of us. So I would like to take my time in thanking our participants for attending the webinar and making this a great success and memorable one. I would also like to thank Team SCDD and Team IT for their all-round efforts in giving this webinar series a wide coverage. Last but not the least, thank to all the members of CSI family who have directly or indirectly helped in hosting this webinar series. Thank you so much. Thanks to all of you. Thank you.
Thank you. Thank you all.
Thank you. Thank you.